In this tutorial, we're going to take a look at the solutions or answers for a test review on exponential and logarithmic equations. And in the first part, there's 3 multiple choice. So the first one asks, which of the following is 625 squared to the power of 3, written as a power of 5? So I want to write this starting as a power of 5. So 625 is 5 to the 4th, and if you weren't sure about that, you could bring your handy dandy calculator over and try different powers. There's a shortcut for this, but like 5 cubed is only 125. 5 to the power of 4 is 625, so that's why 524 is as to 5 to the power of 4 is 625. Since we're actually doing logarithms, this is how you would find directly that it's 5 raised to the power of 4 is 625. So you can use logarithms to do that. So we need to write 625 as a power of 5. So it's 5 to the 4th, and then it's squared, and then cubed. Now, power over power rule applies here, so we multiply the exponents. 4 times 2 is 8, times 3 is 24. So this would be the same as 5 raised to the power of 24, which is answer A here. Now, question number 2 asks to write this whole thing as a single power of 2. It's a couple of different, well, 4096 isn't actually a power, well, I guess you could think of it as 4096 to the power of 1. But we want to write this all as a power of 2. So we want to know what 4096 is a power of 2. So again, if I bring my calculator back, I could try different powers of 2, or I could just go the logarithm of 4096 divided by the logarithm, because I want to raise the power of 2. So it tells me it's 2 to the 12th. So 2 raised to the power of 12, there's a check, is 4096. So 4096 is 2 to the 12th, and the cube root means the power of a third. And then we're dividing this, I'm writing it all over here, as now, again, I want to write this as the power of 2. So 4 is 2 squared. The power, the 5th root means the power of 1/5, and then everything's raised to the power of 7. So 12 times a third, or 12 divided by 3, is 4. So this would be 2 raised to the power of 4 divided by, and so we would have 2. Now I got to multiply 2 by a 5th, so that would be 2/5. And then I'm going to multiply that by the 7. Now remember, 7 is the same as 7 over 1, so that's going to be an exponent of 14/5. Now when you're dividing, you subtract the exponents to raise a single power. So this 4 here actually has a denominator of 1, so I can't write there. I would want to take that 4 over 1 and multiply it by 5 top and bottom, so I have a common denominator with my 14/5 over here, times 5. So that's going to be 20 over 5. So where do I want to write this? We'll keep on going this way. 2 to the 25ths divided by 2 to the 14/5. And you subtract the exponent, so 25ths minus 14/5 would be 6/5, so this is going to be 2 to the 6/5, which is answer D here. Now question 3 here, you're asked to write this big long logarithmic expression as one single logarithm, and notice that they're all base 23. They have to all be the same, or you can't use the laws of logarithms to combine it into single logarithms. So I'm going to use the power law here in all the cases. The 4 comes up, and it's going to be a power of this. I've actually written this down here. In fact, I'm going to move that down a little bit, because I'm going to write a bit below here. I'm just using the space down here for the third multiple choice. So the 4 comes up as a power of the 3w squared. That's what I've written here. And like the 2 will come up as a power of the w to the 5th. That's what I've written here. And the 2/3 will come up as a power of the x to the 9th. And so equals, now I want to simplify this. So I have the logarithm base 23. Now I want to evaluate 3 to the power of 4. So if you don't know that that's 81, you have to evaluate that. So that's going to be 81 first. So this would be 81 w to the 8th. Remember, power of a power rule, so you multiply the 2 and the 4. That's a funny looking 8, but it's an 8. And then plus the logarithm base 23 again. And you multiply the 5 and the 2, so this is going to be a 10. Here, whoops, 10. There we go. Minus, again, log base 23. And now for the exponent of the x, we multiply 9 by 2/3. So 9 times 2/3. See, that 9 is actually 9 over 1. So you multiply the numerators together. 9 and 2 multiply to 18. Over 1 times 3 is 3. So that simplifies to just plain old 6. You'll see people do this, say, oh, well, the 3 goes into the 9 3 times. So this 3 times 2 gives you 6. And it's going to be over 1 times 1 is 1, so it's just 6. So there's a 6 right here. So I want to write this as one single logarithm. So when you're adding two logarithms, actually let me write my log base 23 down first. You multiply this and this together. So it would be 81. And when I multiply w to the 8th by w to the 10th, you add the exponents. Remember, that means that there's 8 w's there and there's 10 more here. So altogether there are 18s. That's why it's the power of 18. And when you're subtracting, then this is going to be over the x to the 6th. Now, since there's a bit of, well, there's a fair bit to this expression, it probably is a good idea to write this in brackets. So it's log base 23 of 81 w to the 18th over x to the 6th. Now, those have different bases, so we can't simplify that. So that is answer B here, log base 23 of 81 to the w to the 18th over 6. So that's why B is the correct answer for question number 3. And, well, we'll just ignore this and won't bother to erase it for question A here. This, of course, has nothing to do with A here. So I want to solve these exponential equations, write answers in exact form only. So the 25 and the 125 can both be written as the powers of 5, base 5. So 25 is 5 squared, and 125 is 5 cubed. So this is really 5 squared to the power of 4x and 5 cubed to the power of negative 7x plus 3. And so we write that as a single power by using the power of a power rule of exponents, or of powers. So we multiply the 2 by the 4x. 2 times 4x is 8x, and same with the 3. 3 gets multiplied into this binomial. So 3 times negative 7x is negative 21x, and of course don't forget the 3 times 3 is going to be 9. Now, I've written these both as powers with the same base. So the only way these two powers can be equal is if this exponent 8x is equal to this exponent negative 21x plus 9. And I want to solve for x here now. So I want to rearrange. I get x's on both sides. So I might add 21x to both sides. So plus 21x here. And so that adds to 0 over here. So that's why there's just 9 left on the right side. 21x and 8x is 29x. And then I'm solving for x. So I would divide both sides, divide it to 29. Divide both sides by 29. So of course the idea on the left here is so that those divide out. I just get x here. And x would equal 9/29. And so that's the answer in exact form. I mean, if you wanted to know what it was as a decimal, 9 divided by 29, that's what it is. Actually, you can the nice thing about doing that, you can actually check in the calculator. So that's my exact value. I mean, if I kept all the decimal places, it's exactly equal to 9 over 29. I don't mean just these digits here, but the ones that keep on going off the screen here. So you can actually check these. If I went 25 to the power of, and I'm putting 4 times that, so 4, and I can go 4 times my last answer. Okay, works out to that. So we have to kind of remember that value. I'm going to do the 9 divided by 29 again so that that decimal, that 0.3103 number is stored in my last answer. So on the right here, I could evaluate 125 to the power of, in brackets, negative 7 times my last answer, that 0.3103 number, plus 3. And notice that we do get exactly the same thing in both cases here. So that's how you can check with your calculator that your answer is correct. And of course, if you did some rounding, then you're not going to get those two values exactly the same, but they'll be pretty close. You'll be able to be pretty confident still your answer's right. Now in B, I cannot write the 8 and 11 as powers of the same base, or not so conveniently as I can with the 25 and 125. So that's why I'm going to use logarithms here. It actually is possible to do that logarithms, but it's probably more complicated than what I've done here, so that's why I'm just going to use logarithms. And so what I'm going to do first is take the logarithm both sides. So that's what I've done here. And since I'm the one doing the taking of the logarithms, I can choose what base I want. My calculator does base 10, so if I want to evaluate the answer using my calculator, I would just use base 10. If you want to use base 8, base 11, or anything else, you could, but I'm just going to write log and it's base 10. And that power rule of logarithms says that we can take this 4x minus 1 and bring it down, and it's multiplied by the log of 8. Same over here, the 7 plus x comes down and is multiplied by the log of 11. And then I'm just doing a little bit of distribute. I'm going to distribute this into the 4x. So 4x times log of 8, and then of course by the negative 1, so it'll be just minus log 8. And the same here, the log of 11 times 7 will be this, and the log of 11 times the x is this term right here. And then the next thing, and I'm trying to isolate for x, so the next thing I'm thinking about is I want to get the terms that have x's on the same side and everything else on the other side. So I rearranged. I'll bring this over to the left, and we could subtract x log 11 to do that. And this doesn't have an x in it, so I want that on the right. So I'm going to add log 8 to both sides, bring it over, it's plus log 8. So basically, that came over here, that came to the right. Now these are the only two terms that have x's, so we can factor an x out. So if I factor an x out of this, the x is gone, it's just 4 log 8, and then the x is gone because I factored it out in log 11, equals this expression. And then to isolate for x, I would divide both sides by this expression. So basically x is this over this, so that's the exact value. Now if you want to use the power rule and like evaluate, bring the 7 up here, and the reason I wouldn't do that is because the numbers get pretty big. Like if you evaluate 11 to the power of 7, then this would be the logarithm of, what would that be? 19,487,171. So a pretty big number. So it's simpler actually, I think, if I leave it in this form. Okay, so I could do that. I could bring the 4 up here, 8 to the power of 4 if I want to as well, but I'm just going to leave it in that form. And again, you could evaluate this and check it in your answer like I did the A one. Okay, that's a way you could check to verify that your answer is correct. On to page 2. A computer virus has infected 30 machines at the beginning of Tuesday at 12 a.m. So it starts with 30 are infected. At 3 a.m., 3 hours later, the estimated number of infected computers is up to 14,800, so it's growing pretty quickly. And you're asked, what is the doubling period in minutes? Now, this is the time's given here in hours, so I'm going to work in hours, and then we'll just convert to minutes at the end. Okay? You can suspect that the doubling period isn't that long because it's growing from 30 to almost 15,000 in a mere 3 hours. But if you wanted to use, instead of 3 hours, the time in minutes, you could. That would be 180 minutes. So I'm going to let V of t represent the number of infected computers after t hours. And if you want, again, t to be in minutes, you could do that too. So this would be my formula. The infected viruses or virus computers is 30 times 2, because it's doubling. I'm looking for the doubling time. 2 to the power of time over the doubling period. So that's just a general formula you'll see used a lot in these kinds of questions. So my amount infected at 3 a.m. is 14,800 and at 3 a.m. so the time would be 3 hours. And again, if you're doing it in minutes, you'd put 180 there. And so I want to isolate for D here. So I want to get the term that has a D in it alone. So I'm going to get this guy alone. Okay. So that's why I would divide the 30 out. So if you take this and divide both sides by 30, and of course the whole point of that is so that these 30s divide out, and so you're just left with a 2 to the power of 3 over d on the right, and 14,800 divided by 30 is 493.3 repeating, so I just kept a few decimal places to maintain some accuracy. And so my variable d is in the exponent, so that's why I would use a logarithm to solve. And the way you rewrite this in log form is the exponent, the 3 over d, is equal to the logarithm of this base 2. Remember, the base of the power is the base, same as the base of the logarithm. Now I'm trying to rearrange for d here, and I didn't show this in the solutions here, but basically what's the simplest way to do this? I guess if you think about cross multiplying, okay, this is over 1, so d multiplied by that log, so d times this log base 2 of 493.3 repeating. I guess I'll write it exactly the same. Okay, so this product is equal to 3 times 1, which of course would be 3. And then to isolate for d, I would divide out this logarithm. So I'll divide out the logarithm base 2 of the 493.333, and the same thing over here. My hand's getting tired writing all this, so I'm going to just go 493. But the idea is the same, 0.3 repeating. So those divide out, so that's why d is equal to 3 divided by that logarithm. So that's what we have in this next line right here. And so d works out to, and I've shown my calculation here. The way you evaluate the logarithm of 493.333 base 2 is if you have a calculator that just does base 10, you go the logarithm of 493.333 divided by the logarithm of the base. And so that's what the denominator is. So that's where we're dividing into 3. So 3 divided by that last answer, that's where the 0.3353 comes from. Okay. So now that's hours. So if I wanted to convert that into minutes, since there are 60 minutes in an hour, we would take that and multiply it by 60. And that's what I'm trying to show right here. So it works out to 20.1, so the doubling time is about 20 minutes, the doubling period. So every 20 minutes there are twice as many computers infected. Question number 3. An 80 milligram sample of radioactive radon-222 decays, and so this is radioactive decay, to 22.46 milligrams in a week. You're asked to determine the half-life of the isotope, and then there's a question on the next page too. So I'm going to call A of t the amount remaining after t days. And so this is my formula. The amount remaining is the initial amount times 2 to the power of, and now if you can't read it, that's negative t over h. It's negative because of the fact that it's decay instead of increasing, like doubling, like the viruses. You'll see some people, instead of writing this, and this is okay, you can write 1/2 instead of 2, and then you don't need the negative in the exponent, and then it would just be t over the half-life. So that's okay. There's nothing wrong with doing that. That's fine. So I want to find the half-life. So we're told this example that in 7 days it goes down to 22.46 milligrams. So 22.46 goes here, and 7 days goes in place of time. You can see the negative a little bit better in that line. And so I want to isolate for h here, and so I want to get this term alone, so I'm dividing out the 80 in the next line. So the 80s divide out, and so I get 2 to the negative 7 over h equals, and that divides to 0.28075, and then I'm going to rewrite it in its equivalent log form. So the exponent, the negative 7 over h, would equal the log of this base 2. And again, I'm isolating for h. So this is actually the same idea as what we did up here. See, notice it actually has exactly the same structure. 3 over d, or negative 7 over h, the variables in the denominator, and this logarithm. So it's really kind of like I can switch those. You see, if I switch the d and the log, then d would equal 3 over the log. Okay, so instead of doing all the cross multiplying, any two things on the diagonal of a proportion can be switched, because like A times B is the same as B times A. So when I go to rearrange for h here, I can bring the h up here and the log underneath, so it's -7 divided by that log. And again, I'm trying to show the calculation over here, -7 divided by the log. So my calculator only does base 10, and I want base 2 though. So I would take the log of this 0.28075 and divide it by the log of 2. Notice my nested brackets here, because I got to evaluate this whole thing before I divide in -7. That's why there's two sets of brackets there. So it gives me 3.8 days. Now, if you want to write that in days and hours instead of 0.8 days, well, what's 0.8 days? If you take the 0.8196, I took a few dozen places and multiply, because it's really 0.8196 or 81.96% of a day. Multiply by 24 hours and gives you 19.6. So it's 3 days and about 20 hours. So that's how long the half-life time is. In 3 days, 20 hours, half of the radions decayed. And for B here, it says how long would it take for the sample to decay to 5 milligrams. So here's my formula. So remember, this is my formula. I now know that H is 3.8. So that formula is exactly what I'm using here. I put 3.8 in place of H. And so I want to know the time for the amount to go down to 5 milligrams. So I put 5 in place of A of t, and I'm going to solve for time. And so I would divide up the 80 first. Again, I want to solve for time, so I want to solve for this in this power here, get the t alone. And so the 80s divide out, so you have 2 to the negative t over 3.8 would equal, and 5 divided by 80 is 0.0625. And so I'm going to, because my unknown, my t, is in the exponent, I'm going to use a log. And so the negative t over 3.8 would equal the log of this base 2. I'm just converting from exponential form to log form. Now, what's different from this one and the last two is that my unknown is in the numerator instead of the denominator. So I can actually, cross-multiplying is relatively simple here, because in order to get the t alone, I can just multiply both sides by, well, I would multiply by negative 3.8. I haven't put the negative there yet. There it is now. And then those would divide out, and so t would equal this logarithm times negative 3.8. So negative 3.8 times that logarithm works out to 15.2. So it takes about 15, just over 15 days for the 80 milligrams to decay down to 5 milligrams. In question number 4, it says simplify each of the following using the laws of logarithms. So write that as a simpler logarithm and as one logarithm as opposed to 2 or 3 different ones. So and of course the bases have to be the same, so that's why these are both log base 9. So that was a 9, that was a 7. I couldn't simplify it at all, other than maybe to evaluate it and find out what it would be as a decimal. So I'm using what's called the quotient rule. The log of 9, log base 9 of 1250 minus the log of base 9 of 50 is the log base 9 of 1250 divided by 50. So I divide the 1250 by 50 and I get 25. And so to write this difference of two logarithms as one single logarithm, it's the logarithm of 25 base 9. For B, I'm going to use the power rule here. The 2 comes up as a power of the 32x to the 10th, so there's the 2/5. And the same with the 4 is going to come up as a power of the 2xy cubed. And so I need to evaluate each of these. Remember, I'm taking the 2/5 power of each of these two things. So the 5 in the bottom here means the root. So this would actually be the 5th root of the 32 raised to the power of 2. 2 again being the numerator is the power. And I'm actually doing the same thing, the x to the 10th, but the simpler way we do that is we use power of power rule. So we multiply the 10 by the 2/5. And now, similar idea here, I can start evaluating the powers because I don't have a fractional exponent here. So I'm going to be doing 2 to the 4th. The x raised to the power of 4 is x to the 4th. And power of a power rule, y cubed to the power of 4, we multiply the 3 and the 4. So 5th root of 32 is 2. And if you're not sure about that, again, we could go back to the calculator. You need to, you need to find this guy here in your calculator. Okay, so number 5 here. So that's what the 5th root. So 5th root of 32 is the number 2, and then we're going to square it. So if I square that, of course, 2 squared is 4. So that's where my 4 comes from here. 10 gets multiplied by the 2/5. So remember, 10 is the same as 10 over 1. So 10 times 2 in the numerator is 20. And in the denominator, 1 times 5 is 5. And that divides evenly. 20 divided by 5 works out to 4. So that's why the x is to the power of 4. Now over here, 2 to the 4th is 16. We have x to the 4th, and I multiply the 3 by the 4 to get 12. And very similar up here, okay, I can write this as one logarithm now that I've simplified these parts, right here and here. It's the logarithm of this over this. So this would be the logarithm of 4x to the 4th over the 16x to the 4th y to the 12th. So 4 goes into 16 4 times. The x to the 4th divide out. So the top divided out completely. Now, there's still a 1 there. Common mistake might be to write that as a 0, but you've actually done this in dividing it out. Okay, so 4 goes into that once, and 4 goes into that 4 times. So that's where there's a 4 on the bottom. So there's a 1 on the top. X to the 4th goes into that once, and x to the 4th goes into that once. So we're actually multiplying 1 by 1 in the numerator here. That's why there's still a 1. So in the denominator we have this 4, and then the y to the 12th. There's nothing to divide out with the y to the 12th, so it's just 4y to the 12th in the denominator. So that's how you write that as one single logarithm. On to C here in question number 4. Logarithm base 2 of this trinomial minus logarithm base 2 of this trinomial. And again, it's a subtraction sign, so I'm going to write this over this. So I'm going to factor, and I guess I could have written them over one another first, but I'm going to factor each of these. So here's my factoring of the 6x squared minus 5x minus 4. And I'm going to use decomposition here. There's other ways to factor trinomials, but that's what I'm going to use here. I want to find two numbers that add to -5 or have a sum of -5 and multiply to -24, because the 6 and -4 multiply to -24. And those numbers would be -3 and, -8 and +3. So I'm going to break that -5x down to -8x plus 3x. And I can common factor a 2x here out of these two. So factor a 2x out of this, I get 3x. Factor a 2x out of that, I get -4. And there's only a common factor of 1 here. If you want to write it, you can put a 1 right there, and that's okay. So 3x minus 4s are both the same, so that common factors out, and 2x plus 1 is the other factor. So that's why I've replaced this with 3x minus 4, 2x plus 1, so that's what's going to be in my numerator. Now we'll also want to factor this, so the 3x squared minus 10x plus 8, what adds -10 and multiplies to, in this case, +24, because 8 and 3 multiply to 24. -4 and -6 do that. And so I can factor just an x out of the first two, get 3x minus 4, and I can factor a -2 out of these to get 3x minus 4. Again, those are the same, so that factors out. X minus 2 is the other one. So that factors into 3x minus 4, x minus 2. So that's what's going to be in my denominator. And since they have this 3x minus 4 factor in common, just like I divide it like the x to the 4ths over here, those will divide out, so it's going to be logarithm base 2 of just 2x plus 1 over x minus 2. That would be the simplest way to write that expression. Question number 5 has to solve each of the following, and you should always check to see if there's any extraneous roots. I think that happens once here in one of these questions. So extraneous roots are roots that you seem to get from the equation, solving the equation, but when you look back, you can see they can't be actual solutions to the original equation. So similar to what we were doing on the previous page, in this we didn't have any of the plus ones, but this is the logarithm, the sum of two logarithms. So write it as one logarithm by taking the log of this and multiplying, well, the log of this times this. So multiplying the x plus 1 and the 2x minus 1. Again, both base 5. So notice I have the logarithm of that product. And to solve this, I'm going to rewrite this back in its equivalent exponential form. So the exponential form would be that this is equal to 5 raised to the power of 1. So that's where the 5 comes from. We don't normally write exponents of 1, but that 1 is that 1 right there. So this will equal 5 to the power of 1, which of course is 5. So I multiply these together. X times 2x is 2x squared. 1 times 2x, maybe I'll write this part out, would be 2x. And then the other product here is a minus x. And 2x minus 1x is x. And 1 times negative 1 is negative 1. Equals to 5. So subtract 5 from both sides, or bring the 5 over and subtract it from the negative 1, which is negative 6. And so I'm going to use decomposition to factor this. I'd be looking for two numbers with a sum of the 1 here from the 1x and a product of 2 times negative 6 is negative 12. And that would be 4 and negative 3. So that's why I'm breaking the 1x down to 4x minus 3x. So I can common factor a 2x out of these two terms. 2x out, this would be x plus 2. And I can factor a negative 3 out of those. So negative 3 out of that would be an x. Negative 3 out of that would be a 2. Notice these are the same. So x plus 2 factors out, and 2x minus 3 is the other factor. So I set each to 0. If I set this to 0, I get negative 2 for a solution. If I set this to 0, I'll get 3/2. And again, maybe I'll do that one because it's fraction. So 2x minus 3. We're going to set that equal to 0. So when we bring the 3 over, remember it changes its sign. Some people you'll see just adding 3 to both sides here. So it equals 3. And divide out to 2. So these 2's divide out, and so 3/2, that's where I get my 3/2 solution. Now, the 3/2 is actually the only legitimate solution here. The negative 2 isn't. It's a solution to this quadratic, but if I put a negative here in place of x, this is what happens. So I'm looking at the first logarithm of my equation. The second one's okay, actually. Oh, no, actually, I guess it isn't. So I didn't bother to do the second one. So I put negative 2 in here. Negative 2 plus 1 is negative 1. So I'm trying to take the logarithm of a negative, which you cannot do. That's undefined. So 3/2 is the only solution. You see, if I put 3/2 in here, 3/2 plus 1 is a positive value, I can take the log of it. If I do 2 times 3/2, okay, that's actually 3, minus 1 is 2. That's actually a positive value, so I can take the log of it. And so 3/2 works. It's okay. But the negative 2 actually makes both the logarithms negative, or what you're taking the logarithm of negative, which you cannot do. You only really need to write one of these, even though it's actually undefined in both logarithms. For question B here, we have the difference of two logarithms, like some of the questions, the simplifying ones on the previous page. So to rewrite as one logarithm, that's what you want to do first here. It's going to be the logarithm of this over this equals to 2. So I'm going to convert back to an exponential form to get an equation that I can solve. So basically this, the x plus 2 over 3x minus 6, would equal 3 raised to the power of 2. So that's my exponential form of this log form. And 3 squared is 9, so that's where my 9 comes from. Now, I'm thinking of that 9 as 9 over 1 here. So the product on this diagonal, which is what I'm doing here, 9 times the 3x minus 6, would equal the product of the x plus 2 times this 1, which is just x plus 2. And so the 9 gets multiplied into the 3x, so that'd be 27x, and 9 times negative 6 is negative 54, equals the x plus 2. I'm trying to solve for x, so the next thing I want to do is get my x terms on one side, my numbers on the other. So I would subtract x from both sides, so there's my minus x, or bring the x over and it's negative. I'd add 54 to both sides, or bring the negative 54, it's going to be a positive 54 over here. 2 and 54 add to 56, 27x minus 1x is 26x. And so I want to solve for x here, so the next thing I would do is divide out the 26, like that. And of course the whole point is so that those x's divide out. And I get x alone, 56 over 26, which reduces to 28/13. I could divide both of these by 2 and get 28 over 13. C. This in C here is kind of a quadratic exponential equation. 2 and then you can think of that as the quadratic term, and this is the linear term. So you can actually factor it in that form, but what a lot of people find simpler to do is to make a substitution. So I'm going to I'm going to call it A. And so the only difference between this and what's in here is it's actually that value squared, because if you take 2x, 2 to the power of x, sorry, and square it, remember you multiply the exponents, so when I multiply the 2 by the x, that's where the 2x comes from here. So if I let a be 2x, then this would actually be 2, okay, well actually here's my equation here. So this would actually be a squared, so that's 2, and then that's a squared, and I'm calling this a. So the equation becomes 2a squared minus 21a plus 40 equals 0. And I want to factor this. So I'm going to do decomposition again. So in order to factor this, I'd be looking for two numbers with a sum of the negative 21 and a product. I'll abbreviate product. 2 times 40 is 80. And so the numbers that fit that, you can click in the right place, are negative 16 and negative 5. Negative 16 and negative 5 multiply to positive 80 and add to negative 21. So that's how I can decompose the negative 21a down to negative 16a minus 5a. So in these two terms, I can factor a 2a out. So if I factor a 2a out of this, I get a. 2a out of this, I get minus 8. And there's a common factor of negative 5 in these, so a factor of negative 5 out of this, I get a. Negative 5 out of this, I get negative 8. It's actually negative 40 divided by negative 5, which is negative 8. So a minus 8 factors out, and then 2a minus 5 is the other factor. And so I set each of these to 0. If I set this to 0, I get 8. If I set this to 0, I get 5 over 2. It's actually just the opposite of this over this. Very similar to what I showed here when I set this one to 0. Now, we said, so remember, we're trying to solve for x here, because the original equation had x's in it. So remember, a was 2 to the x. So the 2 to the x put in place of the a, 2 to the x would equal 8. And so x would be 3, because 2 raised to the power of 3 is 8. So that's a solution. And then 2 to the x would also equal this 5 halves. We're not going to get a nice whole number value for that one. But to rearrange and put this in the equivalent, to solve for x, because x is the exponent, we're going to put it as the equivalent log form. So x would be the log of this base 2. And if you want to evaluate that, you could. So it might be simplest just to do 5 divided by 2. See, 5 divided by 2 is 2.5. So it's the log of that 2.5 divided by the log of 2, because that's the base. So that's where my 1.322 number comes from. And again, we could check that in the equation just to verify that it's correct. Well, actually, let's do that one. Okay, so that's going to be my answer. So I could go 2 times 2 to the power of, okay, 2 times my answer, so 2 times my last answer, close bracket, minus 21 times 2 to the power of just the last answer, not multiplied by anything, and then plus 40. And why do I get negative 1.92? Well, I just learned that I don't know how to use my calculator properly, at least to do this. This is the problem right here. The calculator doesn't know that I wanted to multiply that 1.322 number by 2 before it raises this 2 to that power. So, okay, I'm going to go back and edit this. So I need to put brackets around this. Bracket there, and then I need another set of brackets here to close it. Oh, I messed up. Bracket, insert, there we go. Okay, that's right now. And I get 34.6. What did I do wrong here? Okay, bracket. And that didn't work because, oh, that didn't work because my my answer has been changed. Okay, so let's go back and start that over again. So the 5 divided by 2 is 2.5. So we take the log of that, 2.5 divided by the log of 2. Just to get, I want that exact value in my answer. Okay, so now I'm going to go 2 times 2 raised, and this is where I made the mistake first. I have to go 2 times that last answer. Okay, so that closed that bracket, and I need another bracket to close this one. Now, minus 21 times 2 to the power of that last answer, close that bracket, and then plus 40. And it does work, it does equal 0. Okay, so it was because I had forgotten to put, or I hadn't realized to put the brackets around there. So my calculator just didn't understand that. Calculation. Okay, question number 6. A very infectious disease, you might guess from this question that I'm a Walking Dead fan, has broken out in a populated area. The disease changes people into zombies, in case you haven't watched any zombie movies, and is spread by a healthy human being bitten by an infected zombie. The number of infected grows according to the table at the right. So time is given in hours here, 0 hours to 30, and we start with 25 zombies, and it raises to 1,275 after 30 hours. So we're asked to find an exponential fit to this data using either a graphing calculator or a GeoGebra, and I'm going to show both of them here. I've actually put the screenshots in here, but I'm going to show how this works. I'm just starting the GeoGebra application right now. And it'll be started shortly. Okay, so here's my GeoGebra application. And we want to type in this data first of all. So if you go to spreadsheet, you'll get this spreadsheet looking thing over here. So here's where you type in the 0 hours, 5 hours, 10. Okay, and then we'll go over here and type in these numbers. So 25, 46, 93, etc. Okay, so let me just have a look here, make sure that I type those all in correctly. Yeah, okay. So this is what we want to find an exponential model to fit, exponential equation. So if you go in here and you want two variable regression analysis, because we have two variables who are we're relating the number of infected people to time. So, and just click on Analyze here, and then you have to pick which regression model it is. Okay, so growth is the one that you want. Okay, might actually default it to this here anyway, because of the fact that I've already done this. Okay, well, oh, sorry, I'm looking at the what's on the PDF here. So you click on growth, and see, that's where that equation comes from. So this is the model here. The population is 24.54, almost exactly the initial amount, times 1.14 to the power of x. So that's how you do this with GeoGebra. If you have a graphing calculator, I'll bring the graphing calculator in here and do this too. So you go into Stat and into Edit, and if there's anything in these lists, you want to clear them. So I'm going to go up and clear, hit Enter. Don't hit Delete, or you actually delete the list. You can put it back, but you don't really need to do that. So 0, 5, again, you have to input the data. Okay, I want to go over here now. So my 25, I'm going to use the keyboard on my calculator. On my computer, it's a little bit quicker. There we go. And did we do everything correctly? Did I do everything correctly? 25, 46. looks good. So back into stat and over to calculate. There's all kinds of regression models here, lines, quadratics, cubics, etc. Now, I'll take this off for a second. I do suggest here, if you use the TI family, to use the exponential one. Okay, so that's the kind of model we're looking for. And so if you scroll down, you'll find it here. That's the one right there. Hit enter. Now, it actually defaults to picking stuff from the first two lists, but if you had them in different lists, you could go second, see the list 1 right there, comma, and list 2. And so there's my formula. So A is 24.54. Okay. So same thing the GeoGebra gave me times 1.14 of the x. You see the b value would be 1.14. Okay, so same equation exactly. There's my screenshots, of course, from my calculator too. In my equation, just to write it out, I'm going to let n of t be the number of walkers, infected ones, at t hours. So the regression equation would be n of t equals the 24.54 times 1.14 to the power of time. And it says in B, you're asked, using your model from A, determine the approximate number of walkers after 6 days. And then explain why this is not a reasonable answer. Now, 6 days is, because we're in hours here, 6 times 24 is 144 hours. So if we plug 144 in place of time and evaluate this, we get a little over 3.8 billion. So that would be the amount. That's what the formula gives us. Now, that isn't probably a reasonable answer here, because 3.8 billion, if you know how many people are on the planet Earth, is actually a little more than half the current population. Okay, so you see, people get infected by being bitten by a zombie. So at a certain point, there's getting to be a fair amount of people infected, and there aren't that many left to be infected. See, the 1.14 means that the infected population is growing at 14% per hour. So eventually you're going to get to a point where the more people are going to be infected at a lower rate, because there aren't that many people left to be infected in any given area. So that's probably why it couldn't continue to grow at 1.14 or at 14% forever, because eventually everybody's going to be infected, or a very large percentage of the population will be affected. Okay, last question, number 7 here. An investment starts at $1,200. Interest is compounded monthly. We're told the annual rate is 4.5%. So in A, you're asked to find an equation that relates the original amount, the interest rate, and the time. So this is the compound interest formula. The accumulated amount is the principal times 1 plus the interest rate to the power of the number of compounding periods. And the compounding periods here is monthly, so time is actually in months. Now, to calculate I, since that's annual, but we're doing this monthly, you divide that 4.5%, 0.045, by 12. So it's actually going to be 0.00375% per month. So that goes in place of I, so 1 plus that is 1.00375 to the power of n. So that's what relates the accumulated amount of your investment to the number of compounding periods. And so in B here, and of course, if you wanted to know how much you have at a certain amount of time, if you want to know how much you have after, let's say, 3 years, 3 years is 36 months, you just plug 36 in place of n. But question B asks, how long will it take for the original amount to double? Now, in the question it says we started with $1,200, so that's the original amount there. So $1,200 doubled would be $2,400, so we put $2,400 in place of A and solve for n. So I want to get the term, the power with n in it alone, so I want to get rid of this $1,200. So the first thing I would do is divide both sides by $1,200. Well, the first thing after subbing $2,400 in place of A. So I divide the $1,200 out. $2,400 divided by $1,200 is 2. And so it equals 1.00375 to the power of n. So to solve for n, n's in the exponent, so we need a log. So n would equal the log of 2 base 1.00375. Remember, the base of the exponential form, or the power, is the base of the logarithm. And so I've got this over here anyway, but I'll show it just once again. So the log of 2 divided by the log of that 1.00375 is 185 months. That'd be months because my time's in months. Now that's a lot of months. So if we divide that by 12, so it's 15 years and a bit poor, like 0.432 years. So if I subtract 15 from that, say I want to figure out how many months that is. So that's a fraction of a year, 0.432 years. So if I multiply that by 12, so it's a little over 5 months. So the 15 years and 5 months is how long it would take that amount to double. And that's the end of the tutorial.